Hello there, welcome to our BridgeOpt Shiny application. In this video, I'm going to give you a quick demonstrations of how our Shiny app works. The tool is designed to help you optimize the selection of bridge samples for correcting batch effects in all input proteomics studies. And the tool is primarily based on a simulation-driven approach. The idea of understanding optimal bridge sample selection actually came while we were collecting some samples from Olink Proteomics company. Okay, before I actually show you how you can use the tool, first and foremost, let me describe what is batch effect, what is bridge samples, how the Olink method works for correcting batch effect. Then I'll come back this tool to explain how you can select optimal bridge sample size. Batch effect refers to systematic differences in data that arise due to technical, experimental, or processing variations rather than true biological differences. As batch effect can introduce artificial variation in your dataset, the first thing you should do before you combine the batches and do any kind of downstream analysis is to remove the batch effect. And to address this batch effect issues, Olink recommends replicating some samples between batches, which we refer to here as bridge samples. For example, in one of my research projects, at first we had like 40 samples of patients in batch 1. Then we select 8 samples from batch 1 and rerun those samples while collecting another batch with 40 samples. And the 8 samples that we repeat in batches are bridge samples. Olink recommended a strategy how you should select those bridge samples with Olink bridge selector function in R, where it ensures samples with different mean expression value being selected across ranges of the data. And also try to ensure, criteria like quality control or having lower limit of detection, etc. The main idea here is that the way it works, it actually tries to ensure that all the bridge sample should not select it from one single cluster of your dataset. Then the major question is how many bridge sample to select. Well, depending on the Olink proteomics panel, Olink has different recommendation. Here I have the website where they have all sorts of recommendation. For example, um, for target 96 panel where you have like 92 proteins, their recommendation is like to have 8 to 16 bridge sample. So depending on the Olink panel, you may have more bridging sample recommendation. Now the question was like, is it worth it to spend that amount of money? Or, what is the rational recommendation or statistical justification for this recommendation? To answer all these questions, we came up with all the simulations driven framework idea and the Shiny App tool to find the optimal bridge sample size. Okay, furthermore, Olink has a function called Olink normalization in R. And the way this method works, it utilizes median differences from bridge samples to correct the batch effect. It considers one batch as a reference and the remaining batch to adjust on the reference batch. That is how you try to correct the batch effect. Now let's go back to our Shiny app and let's see how the Shiny app works to find the optimal bridge sample size to correct the batch effect efficiently. All right. As a first step in this Shiny app, what you need to do is to choose the study design. Where design one is the most common, where you can have both case and control in each batch. If you want, you can also select design two, depending on your study design, where in one batch you have only cases, and in another batches you have only controls. I'm going to show here design one as an example. One idea here to note here is that here you need to select all source of parameters so we can generate data set in our simulation design. And also as a downstream analysis, the tool is going to run a two sample t-test as a differential analysis test. And to compare the performance, you're going to have simulated power, type 1 error, false discovery rate. Alright, so initially, you need to select the number of samples in each batch after you select the study design. Here I have, as an example, I have selected 100 in batch 1, 100 in batch 2, and then you need to select the case and control proportion of each batch. And by default here, I have given here like case and control, like 70% cases means 30% control in batch one, and 30% case and 70% control in batch two. Next, you can select number of proteins or number of assays. Well, depending on the holding panel you have, here you can have different number. But let's just consider 100 for now as an example. Moving forward, you can consider, how many assays or proteins you would like to have similar or non-differential in your simulation. So when I say 50 out of 100 means the case and control mean for those proteins would be exactly same in our simulation design. And the remaining 50 would be like differential, means the case and control mean value for those proteins would be different in our simulation. So that is the ground truth in our simulation. Okay, at next step, number of iterations. So depending on the number of iterations you're going to select is going to be computationally more expensive. Our recommendation is to run for 30 iterations at least, so that you can have stable result even though it is computationally expensive. Then you can select number of effect size you may have. Well, you can run it for only one effect size as well if you want, but I guess it's a good idea to see how the optimal bridge size recommendations looks like for different effect size. Then you can select number of bridge sample sizes to test. So here I have even number from 2 to 30, and here 30 should be enough as a maximum number, but if you want, you can test it even higher number than 30. So our tool is going to suggest you between 2 to 30 what is the optimal bridge size. And these suggestions came through simulated power and simulated type 1 error. All right. Then we can have more data generation parameters like like proteins will have mean from 2 to 20 normalized protein expression value. And to construct the covariance matrix in our simulation, there will be diagonal variance, which is a range from 0.1 to 4. And the pairwise correlation will be 0.1 to 0.6. Although these options are complicated to understand, you can just keep it default the way it is, as we try to follow the default value, what we observe in the data set, specifically for these types of parameter, which is based on the data generations of our simulation. And then you can have like significance level that will allow you to do the statistical test to make a decision whether you're going to accept, you are going to reject or not reject in the null hypothesis. Okay, then very important questions. What batch effect to expect? We would say standard batch effect parameter, because it is more stronger than what we observe in three real data set. Also, it has moderate value of batch effect strength in terms of a metric we use called dispersion separability criteria. So our recommendation is to go ahead with the standard batch effect. But if you want, you can also try to be like, try to see how the result looks like when it is strong or weak. And you can also tune the parameters like additive effect, multiplicative effect, and the noise. This parameter determines, how you are creating the batch effect. So let's go ahead with the standard option for now. And then if you hit the simulation button, you can see the progress of your simulation for different iteration, for an effect size, for bridge size. All right, now we have the simulation results that we're looking for, and in different tab of the output in the top, we can see we have different results. So for example, in the detailed result, we have simulation results for all different iteration for every single bridge size, every single effect size. We have different results such as power, type monitor, how the power differences looks like, how the type monitor differences looks like, so you have very detailed result here, which we actually don't need. So let's look at the optimal bridge size result. Here we have for different effect size, we have the optimal bridge size based on the power and based on the type owner. Well, typically, there is, I guess it depends on the research interest as well. Typically, power might be a ideal things to look at, but here we also give you the option to look at how the optimal bridge size looks like if we focus on the type owner. So we're trying to make sure that like after which point the type owner is not um, improving a lot. The same goes to the power. The power we focus on increasing, for the type owner we focus on decreasing. So here if you look at the range for different effect size, it seems like 6 to 16 is an ideal range. If we look at only power, it seems like 12 is the maximum we need to correct batch effect efficiently. Again, don't forget that here we consider a scenario where, which kind of moderately imbalanced across batches. So if we have like a more balanced scenario from our manuscript, we know that we actually don't even need 12 to correct the batch effect. Furthermore, if you look at the power plot or the type 1 plot or the FDR, we can have like more comparison. So the power plot actually gave us the simulated power over all iterations. Um, Again, here the blue line represent for the Olin normalization for different bridge size. It gets brighter when the bridge sample size is higher. The red line is the gold standard line, and the yellow line is when there is no batch correction. And we can see when the bridge sample size is higher, it seems like it is approximately getting towards the red line. The same conclusion we can see for the type 1 plot as well, and similar conclusion we can see for the FDR plot as well. So again, all this plot is going to give you some ideas or some understanding how the result looks like in a simulation. This is how our Shiny app works. And finally, I'd like to say we have a user guide option where you can also see the description of different option works in the Shiny app, which you can read and try to understand as well. So yeah, thank you very much. That's all about our Shiny app.